So in our previous lesson, we learned to approximate the solutions to differential equations by looking at slope fields and by using Euler's method. In this lesson, 8.2, separable equations, we're looking to actually solve those differential equations by using a technique called separating the variables. As a matter of fact, that is the technique that the AP exam is expecting us to perform whenever we solve any differential equation. All right, and on our assignment, take a look here. You do have some bookwork and a supplement. That supplement, another free response question. Give it a try. Let's take a look at our warm-up question. Our first warm-up question. For the differential equation xy prime minus 3y is equal to 0, verify that y equals cx cubed is a solution. Then find the particular solution determined by the initial condition y equals 2 when x is equal to negative 3. All right, and I do have a slope field for that. This is what we talked about in the previous lesson. And we also did the first part of this, which is verifying that y equals cx cubed is actually a solution. And this is what that thing is going to look like when we're all done. It is definitely a cubic equation, as we can see. All right, so I'm going to flip over here and actually verify that that is the case. So we've got... Now this is what? Warm up 1. Our differential equation was xy prime minus 3y, I think, is equal to 0. Yep, looks good. And then we are trying to verify that y equals cx cubed is a solution. So you can see based on the differential equation, which forms a little recipe for us. It's asking for a y and a y prime, so let's find it. So leapfrog the 3 down, I'd have 3cx squared. All right, and now we're good to go to plug everything into the differential equation here. Whoop. So I've got x times the y prime that we just found, 3cx squared, minus 3 times my original y, which is cx cubed, and we're trying to see, is that in fact equal to 0? So multiply on this left-hand side, I get 3cx cubed minus, and then multiply by 3cx cubed. That is in fact equal to 0, so it is a solution. So that first part is verified. And then the second part, find the particular solution determined by the initial condition y equals 2 when x is equal to negative 3. So we've got negative 3 comma 2. I'm going to plug that in and just basically solve that for c. So I've got, let's see, what do we got? Into the equation, y is equal to, so 2 is equal to c times negative 3, and we want to cube that. We would have c times negative 27, so negative 27c. And then finally solve that for c, dividing by negative 27, negative 2 over 27. Okay, so then that means my particular solution is, boop, boop, y is equal to negative 2 over 27, x to the third. All right, so I want to just kind of demonstrate this on our calculator app on TI Inspire, because it'll do such things for us. Oh, before I do that, though, I need to come back up here and take a look at what this differential equation would look like if it was solved for y, because that's how, or y prime, because that's how I have to put it in there. I'd have x y primed is equal to 3y, and then divide the x over, so y prime is equal to 3y over x. That's what I'm going to put in there. Should have had this already pulled up, but I didn't. Okay, let's start a new one. We want a graph, and over here on the tools, on edit and entry, right? Isn't that correct? Yes. Oh, that's correct. And I want a differential equation. I believe it was 3y 1 over, just check, I think it was x, but x, yeah, just x. Over x. And then we did have an initial condition. Our initial condition was don't even remember. Negative 3, 2. Geez, it was like 2 seconds ago. Negative 3, comma 2. Hit enter. All right, there we go. Having a bit of a problem graphing. It looks like part of the solution. Hey, but that's okay. Let's go ahead and add in another graph here. So I'm going to go to a function, and this one was supposed to be negative 2 divided by 27 x to the third, and we should be able to verify this solution. Bam, it matches up perfectly, and you can see that it has a okay time whenever it's solving. When I move the thing, all right, there we go, and we can definitely the equation. All right, that was pretty fun. All right, let's get back to the lesson here. The next warm-up question: which of the following does not belong? So we've got a spectrum of colors here. This red, this orange, this green, this blue. Which one of these differential equations does not belong on this slide? Pause the video. You take a look and you think about it for a second, and then unpause, and I'll tell you the answer. So the one that does not belong is, it's the blue one. And the reason why is because everything else that's on this page, these differential equations are separable equations. What that means is that I can separate the x's from the y's. And that's what we want to be able to do. So I'll demonstrate that right here for each one of these equations. So the first red one here was x squared plus 3y dy dx is equal to 0. I'm going to get x's over on the right, and the y stuff is going to stay. So 3y dy dx is equal to a negative x squared. And I need to get the dx over to the right-hand side too. So I'd have 3y dy is equal to negative x squared dx. And there we go. We have just separated that red equation. All right, and then if I try, let's say the green one here. So the green one is sine x y prime is equal to cosine x. So notice that the sine has an x in it, so it needs to go over to the right-hand side. We'll divide cosine x over sine x. Maybe I go ahead and write that as the cotangent of x, and then rewrite our y prime as a dy dx, cotangent x, and then the last step is to get rid of that dx, bring it over to the other side, so dy is equal to the cotangent of x dx. Definitely separable. All right, and then I think that we had, what, an orange? We did. xy prime over e to the y plus 1 is equal to 2. Yeah, you may hear some beeping in the background. That's dinner being finished. It's probably going to burn by the time I finish this video. Should be nice. All right, the e to the y plus 1, it has a y in it, so it's going to stay. I have to bring the x over to the right-hand side. I'm going to have to divide. So I've got y prime over e to the y plus 1 is equal to 2 over x. So far, so good. And then this y prime is really a dy dx, so I need to get the dx over to the right-hand side, so this becomes a dy over e to the y plus 1 is equal to 2 over x dx. All right, the whole entire reason why we do that is because then we can integrate both sides with respect to, let's say in this case, with respect to y. Oh, those colors look terrible together. And on this side with respect to x. Boom. It's called a separation of variables. Go back to the slideshow for just 1 second. And if I go back over here and look at the blue, there's no way to do that. You cannot get the y prime or the dy, all the y's on one side and the x's. I challenge you to do so. Anyway, here's what we're talking about. Being able to solve differential equations by separating variables. And the next video we'll talk about in detail like the technique that's involved, and then start some examples on solving these differential equations.